Thanks. Let me start by thanking the organizers for having us here in this very nice event. So indeed, I'll be talking to you about the two quantum information tasks, which are the certification of multipartite entanglement and the certification of randomness in the steering scenario, which, as Daniel already said, implies a network of parties in which some parties have knowledge of what they are doing, of the measurements and states that they are doing, and other parties actually have no trust on the devices that they are holding, okay? So the theoretical part of this work was done in ICFO in Barcelona and at the University of Bristol, and the experimental demonstration was made at the Federal University of Rio de Janeiro. So, to start with some motivation about randomness in quantum physics, I guess that, well, a very simple experiment, you will agree, can be thought as a source of randomness. So if we take a beam splitter experiment at the single photon level, and we write the output state after this beam splitter, it's a coherent superposition between the two output arms, right? And then if I simply place some detectors at the output ports, I can see that the process is not non-deterministic in the sense that 50% of the times I will see my photon in one of the output arms, and 50% of the other times I will see it in the other output, right? So this is a non-deterministic process, and in this sense we say it's a random process, right? So actually, based on these simple ideas, there have been commercial enterprises which actually have developed quantum random number generators and also quantum key distribution schemes, for example, based on such quantum information tasks, okay? And you can actually go and buy one of these black boxes which produce quantum random numbers, for instance. But then it turns out that a few years ago, a certain group of people called quantum hackers managed to actually break such systems, right? Using classical resources and without leaving a trace, actually. So, of course, at the beginning, the question, how could this be happening? Is it possible that quantum physics is not correct, or that the security proofs of these devices were not actually correct either? Well, it's not the case, actually. What is happening in the hacking of these devices is that there is occurring a mismatch between the theoretical requirements of the system, of our random number generator. So I'm thinking that my random number generator is a state in a Hilbert space of dimension 2, and I think it's working like this. But actually, when I look at the implementation, probably I would open my black box and I would see that inside my black box there is something like this, no? So it's actually such a mismatch that occurs between the theory and the implementation, which is creating a breach for hacking attacks, no? And this is something fundamental, but also very important in quantum information, no? For having real implementable and useful quantum information protocols, right? So what are the solutions to this problem? So solution A would be to really try to guarantee that somehow whatever we are doing in the lab is really being controlled, that all noise sources are being characterized and taken into account. But perhaps a more, at least from the theoretical side, a more elegant solution is to go to this so-called device-independent framework, no? In which you would like to have still to be able to guarantee that your numbers are random, or that you are distributing a secret key without having to worry much about what's happening inside your device. So this device-independent framework is actually has been quite studied in the recent years. It's mostly based on the idea of Bell non-locality. So the idea is, as we said, that we treat our devices as black boxes, in which we have some inputs on the boxes, which are classical labels, X and Y, and the boxes produce some outcomes, which are A and B. And for example, we might be interested in certifying that this outcome is truly random, or that these two outcomes are produced as secret key, for example, regardless of the actual state that was inside the box. No? So the state could actually be, no matter which state, prepared by a malicious agent, for instance. So as I said, these protocols exist based on Bell non-locality. No? So the idea is that when you violate a Bell inequality, you actually bound the predictability of no matter which person is trying to guess the outcome of the boxes, for example. Okay? So indeed, now this idea provides a ultimate level of security in some sense. So it's like a real paranoid and extremely secure idea for certifying randomness or generating a key. But it has turned out that it's actually very difficult to implement because, as you may know, there are loopholes in Bell experiments which are difficult to close and which are needed to be closed so that we can guarantee security or randomness in such an experiment, okay? So perhaps there is a solution C, which is the one that we would be looking forward here, which would be perhaps to have an intermediate step between the fully device independent and the previous approach, okay? So in this case, as Daniel already said, we are working basing on steering, not on non-locality. So the idea in steering is that instead of working with correlations, with probability distributions at the black box level, we will have such correlations for one of the parties, or for some of the parties, we will have black boxes, again with some classic labels and some classic outputs. But for the white boxes, we will assume that they are characterized, so they are trusted, in the sense that we know that, for instance, the white box B here is actually receiving a state which is the reduced state conditioned on the measurements, on some unknown measurements of Alice being performed on some unknown state row. So the state row and the measurement of Alice are kept unknown and uncharacterized, but however, the reduced state of Bob is now something that can be considered as an element of trust. Well, this could be, for instance, interesting and justifiable in some experiments, for instance, in which, for some reason, you might have 2 degrees of freedom for 2 qubits, and maybe one of them you have some trust on one of your devices, but for experimental reasons, on some other, on the other one, you may not have control, no? And well, maybe it could be, you could, for example, think of a scenario in which this is a trusted bank, no? Well, I don't know if you trust your bank. I don't know if you trust your bank, but you could think of a trusted provider, and on the other side, you have black boxes which would be given to you by the bank, but somehow you don't know the working, but you have the promise that this white box somewhere is actually doing whatever you would be expecting to. So far, well, for the future, we have some ideas for QKD, and yeah, okay, I'll get into that soon. So yeah, and actually the hope here in the EPR steering is that, that the requirements will be more feasible for experiments, and also perhaps more justified, no? As the question of Miguel was suggesting, in the sense that probably in a given experiment, for some sides of my experiment, I cannot have control, but perhaps for another part, which maybe this is a photon and I don't know what is happening, but perhaps this is an atom in a cavity, and there I can have more control on the quantum state that I'm holding, for instance. So these ideas might suggest that we could actually go beyond the bipartite case in the steering scenario, which is actually what we want here. So to think of a network, of a steering network, in the sense that the blue the blue nodes would be trusted, characterized, and the other ones would be black boxes, no? Device independent, no? And in fact, we could think of entanglement detection, random number generation, and perhaps, yes, semi-DIQKD. Perhaps you could think that these two guys want to establish a shared key. So these guys are device independent, but they are still somehow relying on a trusted provider, somehow, something like this. So in this work, we are focusing not yet on the QKD part, but on the entanglement detection and the random number generation. Okay, so yeah, we will also focus on the tripartite case, of course, for simplicity. So in the tripartite case, you have three boxes, right? And you have two possible steering scenarios, right? Either one untrusted box or two untrusted, okay? So in the case of one untrusted, you have a reduced state for boxes B and C, which is conditioned on the outcome A and the input X of the box, of the first box. And if now I think that I have two untrusted parties or two uncharacterized parties, in that case, the state that the white box C receives is conditioned now on measurements both of X and Y on the two first boxes, right? So now let me tell you in a hand-wavy way the way in which we construct the witness, which is actually similar to the construction for the teleportation scheme. So the idea again is, as you know, we know how to construct witnesses by establishing a difference between the set of separable states and the set of entangled states, okay? So here, now we are interested in the set of assemblages, which are these conditioned states that we have. And the idea is that if I take a particular separability notion, like genuine separability across a bipartition or full separability, then these will impose some constraints on the assemblages that Alice and Bob observe, okay? So this set is the set of assemblages coming from any separable row set for a given kind of separability that I want to test. And then the idea is now to work in this space of assemblages and forget about the space of states. And the idea is, again, to characterize this new set with SDP constraints for numerical reasons, mostly. So in some cases, we have to do some relaxations, as we were discussing before, like PPT relaxations. And in other cases, we already have a good, an exact characterization. And then the idea is to simply write an SDP where we want to find the maximal value W that we can add of noise. So we can think of adding noise, of white noise, but not in the space of states, but in the space of assemblages. So what is the maximum amount of noise that I can add to some observed assemblage that the trusted parties see, such that this convex combination of the observed assemblage with my noise in this space belongs to this set of unsteerable assemblages, right? So whenever I get a strictly negative solution, I can actually certify that there is steering, and therefore that the original state was entangled, okay? And because of the dual formulation of semi-definite programs, this actually gives us automatically a witness, which is just a linear function acting on the observed state and giving us the desired optimal violation, okay? Just something we have to be careful here is that, of course, also as Daniel said, there are some entangled states which do not demonstrate steering, and also because in some cases we are relaxing our set, there might be some entangled states which might not be detected. Okay, we don't have concrete examples of this, but it could actually happen. No, but of course, whenever I observe a violation, I do indeed have the certainty that my original state was entangled. So now to tell you a bit about the experiment. Okay, perhaps before telling you about the experiment, since I have some time, okay, of course, very quickly, the notions of entanglement in tripartite systems are, you can check for entanglement in the reduced state, you can check for entanglement in the full state, or you can check for genuine multipartite entanglement, right? Which is whenever the state cannot be written as a convex combination of all bisubprobabilities. And for example, let's say that I want to try to test for tripartite entanglement with one untrusted party. Well, in this case, I have my assemblages which are written in this form. I want to try to test for entanglement, so I take this notion of separability, which is full separability. I insert my notion of separability in my assemblage, and I obtain a decomposition for my assemblage which has this specific form, and from which I can construct my new set of unsteerable states, no? In which I have some conditions, no? And here, as you can see, I have a partial transposition, no? To guarantee separability of these guys, for instance. Okay, so now let me tell you quickly about the experimental part, which was done here in Brazil, in Rio. So the idea was to produce a W state, firstly because the W state contains all types of entanglement, right? Also because the reduced state of the W is still interesting because we don't know if actually it is non-local. So perhaps we can say if it's steerable, if it can demonstrate steering. And of course, it's also an interesting state in general in quantum information, in part because it's a symmetric state among three parts. So we start by preparing a partially entangled state in polarization. Okay, so here we have then our two qubits. And then to obtain the third qubit, we use the path degree of freedom of the second qubit. Okay, so by using beam displacers, we can think that initially our third qubit is in some ancillary state, which is the first path. But now I get my second part of the qubit, and then simply by playing with quarter wave plates and half wave plates, I can perform poly measurements on my three qubits and measure them with photodetectors. Okay, so this is the experiment. The measurements that we perform on this W state were the Pauli observables, so sigma x, sigma y, and sigma z. And now we can apply our methods, right? But actually not so fast. We have just a small issue which is actually interesting because it occurs in any possible experiment that you can think of, which is the fact that actually the observed data that we get from the experiment, actually it's never physical data in the sense that it always has some signaling. And sometimes also you can have a negative eigenvalues, right? In your state, no? So the problem is that you cannot actually solve an SDP program if your input data is not physical, no? So the way we found to actually assess this problem is a three-step method, no? First, the idea is to find with a least square optimization the closest physical assemblage, so the physical assemblage which satisfies non-signaling and which satisfies positivity constraint, which is closest to the observed data, okay? Which is not physical. Then, now once we have our physical assemblage, we can solve our SDP, okay? And this SDP will give us a proper witness, no? Which is W physical. And finally, we can come back to the experimental data by applying the physical witness to the observed assemblage, no? And this gives us the experimental violation. So the results are that we managed to certify all types of entanglement, both for the case of one untrusted party and for the case of two untrusted. So we have entanglement in the reduced state, entanglements in general, and genuine multipartite entanglement. And what is interesting to see here is that a more demanding task gives you a smaller violation, no? Because this violation can be also, as I said, thought as the amount of noise that you have to add such that the state becomes separable, unsteerable, the assemblage. Okay, so this was the entanglement part. So in the time that I have left, I will tell you a little bit about the randomness part. So, yeah. Yes, exactly. Yes, and exactly. So here in the reductions, you don't trust one of the part, and the other you completely discard it. No? So actually, this other part could either be trusted or untrusted, and actually, this is very demanding if you think, no, because you are testing both whenever the other part is trusted or not trusted, and actually, this is why this violation is so small, no? Because it's actually more demanding than what you could think. No, yeah, well, perhaps we haven't thought much about this, but so far we are using all the data to, yeah. Okay. So, okay, so exactly, this is the scenario that Rafael was talking about. So in the case where we analyze the reduced state, we completely discard the third party, and no matter if it's trusted or untrusted, and we are only thinking one of the boxes is trusted and the other is not, okay? And what we don't know is if this reduced state is non-local, but because of our results, we know that it is steerable, okay? So it can demonstrate steering. But something interesting that happens, okay, so let me just quickly tell you about the randomness. So what we mean by randomness is to think how easily or how could an eavesdropper who had prepared this black box by preparing the state and the measurements inside this box, how well could she guess the outcome of this box? No? Okay? When she can guess with unit probability this outcome, we have no randomness. But as soon as she has a non-unit guessing probability, we have some randomness. Okay? So this is the idea of device-independent randomness, and in this case we call it one-sided device-independent. No? And the curious part is that in general we have this notion that from any non-local correlations you will have actually some randomness, because somehow the non-locality is telling you that there is some bound on the predictability of your outcomes, right? But a curious phenomenon that occurs here is that even if the state is found to be steerable, when we perform the Pauli measurements on the reduced state, we see no randomness at all, and this is known by some people as bound randomness. So in the full device-independent case, you have non-local correlations, but even if you try to extract randomness, you have nothing from a given setting. So this was a curious fact. But then instead what we did to have one-sided randomness is now to treat the two untrusted boxes as one, okay? And consider the bipartition that is created between the two untrusted and the trusted box. And in this case, in theory, you can certify up to log2 of 3 bits, random bits. But however, this is experimentally very demanding, and the robustness to noise of this randomness certification is very bad. So actually in the experiment, we only managed to certify around to 0.26 random bits. Okay, so with this, Yes, but maybe your boxes are not in the same place, right? So maybe you cannot put everything together, no? So yeah, but imagine that. So you're saying that if I trust my party, I can really generate the randomness in the normal way. But let's say that the party that gave me that is trusted is actually 10 kilometers from here, no? And I have this state shared, so I have to, and I still want to do some device-independent task with one of my box without having to check with my trusted provider, no? Maybe in that scenario it could be justified. So with this, let me conclude. So what we have seen is that separability of quantum states impose SDP constraints on the set of assemblages. That such a membership in this set of assemblages can be witnessed with SDP theory, no? By, in some cases, having to relax the set. And this, in turn, with duality theory, gives us semi-device independent entanglement witnesses. We managed to certify all types of entanglement from the W state in the experiment. We found a curious fact from the, two curious facts from the reduced state. One is that it is steerable, so it's closer to be non-local. We still don't know if it's non-local or not, but at least steering is a step closer to non-locality. But curiously, even if it's steerable, it doesn't possess one-sided randomness. So I cannot extract randomness in this case. But by going to a bipartition of the W state, in theory, I can certify even more than one random bit, although in the experiment, the numbers were not so good for the randoms. So with this, I would like to thank you.